Today we'll be starting chapter 9, which is our first out of two chapters covering the oceans. But when we're talking about the oceans, the first thing that we really need to go over is why they're important on our planet and exactly where they are and what they're named. So if you ever want to study the oceans, you would be studying oceanography, in which you would be looking at all different aspects of our ocean, not only where this water is, but the temperature and the salinity, basically how much salt is inside of the water, and how this water is going to move around to different places of the world over time. But when it comes to our planet, Earth is really unique, and it's known as the blue planet. And this is because so much of the surface of our planet is covered in water. Just under three-quarters of all of our planet is submerged in this salty water that we call our oceans. But if we're looking at our world, there are going to be major differences between the northern hemisphere and the southern hemisphere. So the northern hemisphere where we live, we'll see that almost all of the area in this hemisphere is covered with land. Therefore, we call our northern hemisphere the land hemisphere. But it's going to be the exact opposite if we look at our southern hemisphere, where the South Pole is. In this hemisphere, we see that almost all of the area is covered in oceans. And therefore, we call our southern hemisphere the water hemisphere. When we look at all of the oceans on our planet, there are 5 oceans. But we're going to see that there are 4 main ocean basins. So with an ocean basin, this is just a really large kind of bowl shape depression. So think about like a cereal bowl, how it goes down towards the center. This is how the seafloor looks like in an ocean basin. So we have 5 oceans, but only 4 ocean basins. And that's because our 5th ocean, the Southern Ocean down here by Antarctica, there's no ocean basin. It's all completely flat ocean floor. But the other 4 oceans all have these basins, these bowl-shaped depressions going down towards the center. Now on our planet, the largest ocean is the Pacific Ocean. It's going to stretch from the west coast of the Americas all the way over to the east coast of Asia and Australia. So the Pacific Ocean is our largest ocean. It's not only covering the greatest amount of surface area of our planet, but this is by far the deepest ocean as well. So therefore, because it has so much size and depth, our Pacific Ocean holds the most water out of any of the 5 oceans. But as we continue moving down this list, our oceans are getting smaller and smaller. So after the Pacific Ocean, the next largest is the Atlantic Ocean, which is near where we live. It's separating the Americas away from Africa and from Europe. Our third largest ocean is the Indian Ocean. Here it's located just south of India and is separating most of Asia, Africa, and Australia as well. And then our last major ocean that is in a basin is our Arctic Ocean around our North Pole. But when it comes to talking about our ocean water, we're going to see that there are major differences between each of these oceans, in addition to just where they're located. We're going to see major differences in the salinity, basically how much salt and dissolved substances are stored within that water, as well as differences in the temperature of our water. So when we're talking about salinity, this isn't just the amount of salt in our water. It's any type of solid material that's actually dissolved in the water, so that the particles are so small that we can't see them even with a microscope. But generally, the most common thing that is dissolved in our water is going to be some type of salt. But when we're talking about our salinity, there are going to be 2 different ways that we can measure it. The first is just measuring the water as a percentage. But generally, the amount of salts inside of this salt water is very, very small. So we would be talking about 0.01% salinity. And when we're talking about really small numbers like that, it doesn't really make a lot of sense. So what we generally do, instead of saying a salinity in a percent, instead we express them in parts per thousand. So imagine me just having a cup of water. And in this cup of water, there are 1,000 molecules of water. Let's say that I have a 20 parts per thousand cup of seawater. That means that for every 1,000 molecules of water, there are going to be 20 molecules of salt dissolved inside of that water. It's just a lot better way to express the amount since the amount of salts overall are very small compared to the amount of water in that cup. And we'll see on our next slide that there are lots of different types of salts inside of our seawater. But the most common type is sodium chloride, the same salt that makes up our table salt. But it's not just sodium chloride or our table salt that's in our seawater. It's just the greatest amount of salt. But if we look at this recipe, this is going to tell us not only the types of salts that are found in our ocean waters, but exactly how much salt is inside of it. So as we start up with the top of our list, we see sodium chloride. Again, this is our table salt, but this is the most abundant type of salt. And as we work our way down through this list, you'll see that the amounts of these salts are going to get smaller and smaller until we're talking very, very small amounts. So there are tons of different types of salt in our seawater. But again, the most common type is going to be sodium chloride, or our generic table salt. But where exactly did all of these salts come from? We're going to see that there are two main ways that these salts were added to our oceans. The first of which is just weathering of all of our continents. We know that everything exposed on the surface of our planet is constantly being weathered. Whether it be rain or wind, we're constantly breaking rocks down into smaller pieces. And our continents are made out of those felsic minerals. Those are the ones that are full of salts, not metals. So whenever we have our continents being broken down into smaller and smaller pieces, once those small pieces of continental rocks end up into our oceans, the salts are going to dissolve inside of the water. And this is the most common way that salt is added to our oceans. But we're also going to see that we get some of our salts directly from the mantle of our Earth, not coming from the rocks themselves, but from the mantle, that magma that slowly flows around on the inside of the Earth. Eventually, that magma might erupt through a volcano, which could also add in salts to our ocean water. But although we're constantly adding in more and more salts, whether it be a volcanic eruption or just long-term weathering of our continents, we're going to see that over really long periods of time, like millions of years, the composition or the salinity of our seawater has stayed relatively the same throughout these really long periods of time. And this is because it's not only being added to our oceans every day, but these salts are also being removed just as quickly as they're added. And this is because all living things need some amount of salts in their diet. As humans, you might think that you shouldn't eat a lot of salt, but we still need some salts in order to survive. And all living organisms on the earth, whether it's animals or plants, if they're living in the oceans, they're removing some of these salts as well. So we see that the amount of salts added and the amount of salts being removed every year from our oceans equal each other out. But if we look on short periods of time, instead of millions of years, let's say a year, we're going to see that there are going to be differences in the salinity of our water. So if we start adding in fresh water to an ocean, if we start adding in water that doesn't have any salt, we're going to start seeing that the salinity is going to decrease. We're increasing the amount of water, but we're not adding in more salts. And we're going to be able to add in fresh water from things like precipitation. And eventually that rain is going to move off the continents as our continental runoff. And all continental runoff eventually makes its way back into the oceans. But if we look around our northern and southern poles, where we have a lot of icebergs and sea ice, we're also seeing that this solid ice is melting back into our oceans. When we look at ice, ice cannot freeze with salts inside of it. So if I were to fill an ice tray with salt water and stick it inside of my freezer, when I pull out that ice tray, I'm going to have chunks of ice of fresh water. And once I pop that ice cube out, I'll notice that there's going to be a crust of salt left inside of the tray. And that's because as salt water freezes, it kind of pushes out all the salts, and only fresh water freezes. So once we start melting all of these glaciers and all of the solid ice, it's just releasing fresh water back into our oceans, and therefore decreasing our salinity. But other places, we're going to be removing some of our fresh water. And when we remove our fresh water, that means that overall the amount of salts that are left behind are just going to keep increasing, therefore increasing the salinity of our water. And we're going to see that the two most common ways to remove fresh water from our oceans is from general evaporation. We know that the sun hits the surface of our oceans and causes the water cycle to start by evaporating that upper layer. So when we're evaporating away our seawater, all of these salts that are in it are going to be left behind, therefore making that water more saline or have a higher salinity content. But if we also start forming more sea ice around our poles, again, when ice freezes, it cannot freeze with salts inside of it. So instead, that sea ice is going to be pure water, thereby forcing the remaining liquid water to hold more salts and therefore have a higher salinity. But we don't only want to look at how our ocean water changes from place to place. We also want to know how our ocean waters are going to change with depth. So if we start off at the surface of our oceans, like where we would swim, we want to look at how things are going to change with increasing depth as we go lower and lower inside of our oceans towards the seafloor below them. And one of the first things that we'll notice as we work our way from the surface to deep waters is that our temperature is going to very quickly change. And this is called a thermocline, where thermo means heat and cline always means slope. So at our surface waters, again, we have a lot of sunlight hitting our surface waters, which is going to heat them up. They're going to be very warm waters. But you'll notice that when we start to go deeper inside of our oceans, now our temperature is going to very quickly decrease across this thermocline. And that's because the deeper that we go, we're getting less and less sunlight. Therefore, that water's just going to get colder and colder. But eventually, we're going to be so deep inside of our water that sunlight's not going to be able to reach those depths anymore. And therefore, we're going to end up with this vertical line where our temperature doesn't change, but instead it stays around 2 degrees Celsius no matter how deep you are. Again, because all of this lacks any sunlight. But this is what we see with our low latitudes, places like where we live in Florida. But if we go to a place like the high latitudes, like our north or our south poles, which are found at the top and the bottom of our planet, we are not going to see a thermocline here. And that's because around our poles, we get very little sunlight. Therefore, even at the surface water, all of that water is going to remain very, very cold. But in addition to our temperature, we also want to think about our salinity. And our salinity is going to directly impact the density of our water. So salinity is just measuring how much particles or how many particles are dissolved inside of water. So let's imagine that I have a 5-gallon bucket. Initially, I just pour it straight from my tap. It's going to be pure fresh water. And this fresh water is going to be a low density. But now I'm just going to take an entire bag of sugar and dump it inside of that bucket. Now I'm adding in a lot of solid particles that are going to dissolve. Even though all of the water inside of that bucket is still 5 gallons, I've now increased the amount of molecules inside of that bucket by adding in all of that sugar. So by increasing the number of particles, we increase the density of this water. And salinity works the exact same way. The higher the salinity, the more salts are dissolved inside of a water, which means that each molecule of that water is going to be more densely packed in together. But we also see that our density is going to be influenced by the temperature. So think about camping in two different situations. The first, you're going to go camping outside in the middle of August. It's going to be very warm outside. So to try to cool your body off, even subconsciously, when you try to sleep that night, you're going to stretch out. You're going to decrease the overall density. And water is going to work the same way. We see that hot water wants to stretch out. It wants to get away from the other water molecules. So the higher the temperature, the least dense it's going to be. And the exact opposite is true if we talk about cold water. If you were to sleep, let's say in Alaska, outside in the middle of January, it's going to be very cold. You're going to bring your body together and kind of condense it into a smaller area. We see cold water doing the exact same thing. So cold water with lower temperature is going to have an increased density because all of those molecules are going to try to get into a smaller area. So just like we saw that thermocline where temperature changes with depth, when we're talking about our density, we're going to see something called a pycnocline develop, or basically how does the density of this water change with depth. Along the surface of our oceans, these are the least dense waters. They're warm because they're getting a lot of sunlight, and we also have a lot of rivers discharging fresh water. So our lowest salinity waters in our oceans are always found right along the surface. But as we start increasing in our depth, we'll see that the water is going to very quickly start increasing in density. The deeper that we go, the less sunlight we're getting. Therefore, the colder that water is going to be, and the more it's going to compact into a smaller area. But just like we saw with our thermocline, we also do not have a pycnocline at our high latitudes. And here there's so much ice around our poles that it doesn't matter about the sunlight at the surface. The ice is going to keep that water so cold that it's going to have a high density from the top to the bottom of these ocean waters. So within these slides, you'll notice that there are some blue links present here, shown in these blue text. These are going to be links to YouTube videos that are going to be able to better describe some of these since I don't have access to a whiteboard to kind of draw things out for you. So you can find these YouTube links by looking for these blue underlined text, but I'm also going to add them to our class's YouTube playlist as well. So we're going to see that temperature and salinity differences are going to cause our oceans to create different layers based on their densities. And we're going to see 3 different layers develop: our deep zone layer, a transition zone layer, and our surface mix zone layer. And we're going to start off with our surface mix zone layer. Here, again, we have a lot of sunlight that is hitting these surface waters. Therefore, it's going to be increasing the temperature and therefore decreasing the density. But here we also have a lot of rivers that are discharging fresh water, which will also decrease the density. So this surface mix zone layer, shown here in pink, is a higher temperature, lower salinity water. But now let's jump down to this deep zone. Here we're talking about really deep water, so it doesn't have any sunlight, and it's therefore going to be really cold, but it's also going to be very dense, not only because of the temperature of the water alone, but now this water along the base is underneath a lot of weight from all of the water above it. So it's going to start compacting these water molecules closer together, also increasing the density. So with our deep zone layer, now we're looking at really cold, very dense water. And we have this transition zone layer between them, basically transitioning between our warm, low density water and our very cold, higher density water. But again, if we go to our higher latitudes, closer to our poles, you're going to see that these three layers don't exist. Instead, it's only going to be that deep zone water. Because the closer we get to the poles, not only the colder is it going to be, but the less sunlight we're going to receive, which means that even the surface water closer to our poles is all going to be very cold, very dense water. So now we're going to take a step back from talking about the water specifically in our oceans, and we're going to talk about our continental margins. Basically, how do the continents end up along our ocean floors? So when we look at our different types of continental margins or the edges of our continents, we're going to see two very different types. One is called a passive margin and the other is an active margin. And the main difference between the two is whether or not plate tectonics are currently occurring. Are these plates currently moving or active? In which case it's called an active margin. But if that plate boundary is currently just sitting still, it's not moving towards, away, or sliding past another continent, it's called a passive margin. But depending on which type of continental margin we're looking at, we're going to have very different topographic features, basically very different shapes in our seafloor beneath all of this ocean water. We're going to see things like seamounts, which are just undersea mountains, and abyssal plains, which are these very deep, flat areas of our oceans. But when we look at our major oceans around our planet, we'll notice that all of them also have mid-ocean ridges, which were related to those divergent boundaries, where we had two plates that were diverging or separating from each other, and new crust was forming in the gap between them. So again, when we're talking about these continental margins, it's basically the margin or the edge of our continents. It's where the continental crust or the continental lithosphere stops and the oceanic lithosphere begins. And we have two different types of these continental margins. Here we're looking at an image of the east coast of the US, including Florida. This is a passive margin. Right now, even though this is a plate boundary, this plate boundary is not moving. It's just sitting still and has been for millions of years. Therefore, the east coast of the US has a passive margin. It's just not currently moving around. We're going to see that our passive continental margins are not only just found along the east coast of the United States, but almost around the entire Atlantic Ocean. And this is because the Atlantic plate is not currently moving. It's passive. It is staying still. And because these plate boundaries are not actively moving, that means that we're going to see very little volcanisms and very few earthquakes because both of these geological phenomenon are caused by plates either moving towards, away, or sliding past each other. But the Atlantic Ocean lacks any of this movement. So if we're trying to break our passive continental margin into smaller features, we're going to see three main areas: our shelf, the slope, and then the continental rise. We're going to start off talking about our continental shelf here. So with our continental shelf, this is just parts of our continent that's submerged underneath the water. So think about going to the beach. At some beaches, you can walk pretty far out into the water and still have land underneath your feet. Even though you're in the ocean itself, you are still on top of a continent. That continent just happens to be underneath a little bit of water. So these continental shelves extend far longer than what we could just walk out into. Generally, they're going to go off for maybe a couple hundred miles around the edge of our continent. But the width itself is going to vary a lot. Places like Florida, we're going to see that our continental shelf, shown in this light blue, is almost 3 times the size of the state itself. But other places, like if we go up to Virginia or Delaware, here this continental shelf is very narrow. So the width is going to vary just depending on where you are. But regardless of location, this continental shelf is always going to be relatively flat. It's going to be very gently sloping. So think about the parking lots outside on our campus. But they're also almost completely featureless. They're going to be almost as flat as a table is. So there aren't going to be hills or valleys in our continental shelf. They're just going to be mostly flat. But one of the most important aspects of our continental shelf is that this is where most of our oil, the petroleum that fuels our car, and the natural gas that can fuel our homes, and other really important economic minerals are found. So we know more about our continental shelf, part of our oceans, than the rest of our oceans combined, because there's so much economic importance in these areas. So where our continental shelf ends, we're going to see that our continental slope is going to start. And this continental slope is going to be important in several different ways. The first of which is that it's the transition area as we go from this really thick, buoyant continental crust to our denser, deeper oceanic crust. So it's just a transition between our continental to our oceanic crust, or our felsic to our mafic lithosphere. But what else is important about this continental slope is how incredibly steep it is. So this gradient is so steep that all of the sediment that is falling off the shelf, again, we have rivers over here that are discharging water. This water is not only water itself, but it's also carrying sediment. So once the sediment reaches the top of our slope here, the slope is so steep that the sediment is just going to quickly slide down the side, just like we would if we got on a bike on a really steep hill. And all of that sediment is going to end up in our continental rise. This is basically the very, very edge of our continent before it is entirely oceanic crust beside it. So with this continental rise, it's still sloping, but it's a lot more gentle of a slope than our continental slope was. But here, this is where we're going to have really thick layers of sediment. All of this dirt that came in from our continents is going to start layering up in this continental rise area. So those were our passive continental margins. If we look elsewhere on the Earth, we're going to find our active continental margins, where we have active plate tectonics, so that the plates themselves are actively moving around. And we're generally going to find these active margins around a convergent boundary, where we have two plates that are colliding together. And this is going to be important because we need a subduction zone to develop. We need at least one oceanic plate to be pushed back inside of the Earth. And this is going to create something called a deep sea trench. So if you've ever seen old like World War I movies, our soldiers used to dig these trenches, these deep, really long features into the ground so that they could lay inside of them and be protected from any bullets flying through the air. But we're going to find these same types of trenches, but on a much larger scale inside of our oceans, right along a convergent boundary. And this is because as this plate is being pushed back inside of the Earth, it's going to start pulling down the upper edge of the overriding plate with it. So if we have a convergent boundary and two plates are colliding together, it's not a simple movement downward. Instead, as this plate is being pulled back inside of the Earth, it's going to start pulling this other plate down with it along the edge where they meet. And this is just going to create a V-shaped area, also known as a deep sea or a deep ocean trench. But with these active continental margins, they're found around the Pacific Ocean. And that's because the Pacific plate is surrounded by these convergent boundaries. This is another reason why we see so many volcanic eruptions and earthquakes happening around the Pacific Ocean. We have active tectonic movement in these areas. So this map is just showing us locations around the world where we see our active continental margins, which are shown here with these red triangles. So here we can see that almost all of these active continental margins are found along the edges of our Pacific Ocean. And this is where we also have our Ring of Fire, all of those volcanic eruptions, and where we have our Circum-Pacific Belt, that area where we see most of the earthquakes occurring along the Earth as well. So now we're just going to look at exactly how the seafloor looks like underneath all of these massive amounts of water inside of our deep sea basins. So when we look at our deep sea basins, we're going to see a lot of very specific features that develop, one of which we just talked about, which are our deep ocean or our deep sea trenches. Here we're looking at a map of a small area of the Pacific Ocean. And if you've ever looked at an ocean map, you'll notice that it's going to use very different shades of blue. So regardless of what type of water you're looking at, if you're looking at very light shades of blue, this means that the water is really shallow, from the surface water down to the seafloor. But the darker blue you get, the deeper that water is going to be. So we'll see that based on this map, the Mariana Trench is one of the deepest locations not only in this area, but along the entire planet. And again, these deep sea trenches develop not only at a convergent boundary, but specifically at a subduction zone, where we're forcing one plate to be pulled beneath the next, therefore causing this really deep V-shaped area between them. But when we see these deep sea trenches, we're going to see a lot of volcanic activity occurring. And we're going to have two different types of volcanic chains forming. Some of them are going to form in the middle of our oceans, and they'll be called volcanic island arcs. But other chains of volcanoes are going to form on our continents, and we'll call these continental volcanic arcs. And we'll go over each of these separately in just a few minutes. But in addition to our deep sea trench, we're also going to see abyssal plains developing. These are going to be really deep and incredibly flat areas of our seafloor. So abyssal just means deep and plains mean flat. And we see that these abyssal plains are probably the most level or completely flat places on our entire planet. And that's because these abyssal plains are found along the edges of our continental rise. All of the sediment that's coming into our ocean is going to be sliding down the continental slope, go through the continental rise, and then it's going to start layering up in these abyssal plains. So here we just have really thick, I'm talking about miles thick layers of dirt and sediment sitting on top of our seafloor. But in our deep oceans, we're also going to see things called seamounts developing. And seamounts are just mountains that are underneath the surface of the ocean. But these mountains are generally going to be volcanoes. Remember from earlier chapters that volcanoes are still mountains because a mountain is just anything that is in higher elevation than its surrounding crust. So even though this is underneath the sea, these are still considered mountains. But these seamounts could either be one isolated volcano, or we can have many of them forming together along a change around our ocean ridges. But if our seamount grows, if it's a volcano that erupts time and time again, Eventually the seamount's going to be so large, it's going to go above the surface of the ocean, and then it's going to emerge as an island. So here we're looking at what's called a seismic reflection. Scientists can basically take an X-ray of what it looks like underneath the surface of our planet. And here it's not very clear what's going on. But if we look at a sketch of what this actual real life data shows, we'll see that here, this is our oceanic crust. It's that mafic, really dense, full of metal crust. And it's not level. There are lots of really high places and really low places inside of our crust. But we'll notice that on top of it, we have these layers of sediment. That layer after layer are going to start by filling in the deepest areas, and then eventually, by the time we get to the top layers, it's going to be completely flat. And this is going to form our abyssal plain, those really deep, incredibly flat areas of our seafloor. But here we'll also see that a bit of our crust kind of pokes out of all this dirt, and this would be considered a seamount. And now we're going to wrap up this chapter by talking about our oceanic ridges, which we discussed pretty extensively when we were going over plate tectonics. So these last few slides are basically going to be a review of things that we've gone over before. So our mid-ocean ridges, or just an oceanic ridge, these are found in all of our major oceans across the planet. And that's because these mid-ocean ridges form along our divergent plate boundaries, where you have two plates that are diverging or spreading apart. When they're moving away, there's going to be a gap that develops between them. And we're going to have magma coming up and filling this gap, therefore creating new seafloor between these separating plates. But this new seafloor is not going to be flat. Instead, it's going to be elevated. It's going to have a peak shape to it, which is known as the mid-ocean ridge. And these mid-ocean ridges might not seem important, but it's actually the longest feature in topography on our entire planet. It's covering over 40,000 miles in length. And if we can look underneath all of the water, these mid-ocean ridges cover almost a quarter of the surface of our planet. So when we look at these mid-ocean ridges, one of the first things that we're going to notice is the elevated position in the middle. And then as we go off towards the sides, we'll notice that they get relatively flat. And this is, again, due to the fact that all of this magma is coming up towards the center where these two plates are diverging or separating, forming this newly formed crust that's going to be incredibly hot in temperature between them. But we know that when rocks are hot, just like when we are, these rocks are going to try to stretch out. These rocks, though, are solid. They can't move very easily. So as these rocks start to expand outwards, they're going to start faulting. They're going to start breaking up and being uplifted or just being pushed farther up along the crust. But again, probably the most important part of a mid-ocean ridge is this elevated position in the middle. This is all newly formed crust. It's just cooled off from a liquid magma and turned into a solid rock. So it's incredibly hot. And that hot rock is expanding outwards. Therefore, it's becoming wider and it's becoming taller in elevation. But you'll notice that as we move away from the ridge, now our crust is starting to become fairly flat. That's because as we move away from the ridge, the rocks are getting older and older. And therefore, they've had more time to cool off. And just like us in a really cold environment where we're going to start bundling up, we're going to see that this older, colder crust is going to contract and it's going to become denser. Because it's denser, it's going to start settling out towards the sides, forming these really flat areas.